So in this video we want to go over how to classify differential equations. So differential equations, it turns out, are classified in general based on three characteristics: their order, their type, and their linearity. And so the first thing we'll talk about is order. And order simply says look at the differential equation and find the largest derivative of y that's present in your equation, and that is going to be the order of the differential equation. So if I look at this first differential equation here, I have y, y prime, and y double prime. So here the highest derivative of y that's showing up is the second derivative. So this is a second order differential equation. Here I have d2y dx2, so the second derivative of y, the first derivative of y, and y itself. So this turns out to be a also second order differential equation. Here we have y, y prime, the first derivative of y, the third derivative of y, and the fourth derivative of y. So this is a fourth order differential equation. And here is an important piece for notation. So we want to discriminate between y to the fourth power and y to the fourth derivative. So when we're indicating the fourth derivative of y and we're not using the prime notation that we're accustomed to, you'll put the order of the derivative in a parentheses to distinguish it from the exponent for. So this says fourth derivative. This would be fourth power of y. So if we wanted to raise the fourth derivative to the fourth power, it would need to look something like this. We would take the fourth derivative using the parentheses and then say I have the fourth power of the fourth derivative. And even with the y prime and y triple prime notation, instead of doing y triple prime, I could say this is y, the third derivative of y. So fourth order here. Here I have partial derivatives. So some of you may have seen partial derivatives already, some may not have. So here the function instead of y is the function u, and this is the first derivative of u with respect to t, and this is the second derivative of u with respect to, this should be a t, so that's a typo. Those independent variables need to match, and this would be a second order differential equation. And here I have the first derivative of u, I have the second derivative of u, and so that would make this a third order differential equation. So then we can also identify differential equations by their type, whether we have an ordinary or partial differential equation, and that's just a matter of looking at the differential equation and saying, does it involve partial derivatives, or does it just involve derivatives where we have a single independent variable? So here this is an ordinary differential equation because we're really working with dy dt, d2y dt2. So we have a single independent variable t, and we have the derivatives of y with respect to that variable. This is an ordinary differential equation as well because it also doesn't involve partial derivatives. This is an ordinary differential equation because it involves y as a function of a single variable t and derivatives of y. Here we have functions of two variables, x and t, and this would be a partial derivative. These are partial derivatives here. So we have the partial derivative symbol, partial t. We have partial x, and it was okay on the previous screen to let that be. I was not thinking straight when I spoke, which is unfortunate. Partial derivatives means that we're working with functions of more than one variable. So we can take derivatives of u with respect to either of the two variables, and that would be okay to do. So this would be a partial differential equation, and this is a partial differential equation, or PDE, because it has partial derivatives in it. And the partial derivatives, if you haven't experienced them yet, those are things that you're going to see when you start working with functions of more than one variable. And then the last thing that we can classify differential equations on is their linearity. So linearity, for a differential equation to be linear, we need to be able to write it in this form. And the key is, instead of just reading this to you, we need to look at the coefficients on y and its derivatives. So here's y and the derivatives of y all the way through the nth derivative of y. Again, this is derivative notation, not an exponent, because we have these numbers in parentheses indicating this is the nth derivative of y, this is the n minus first derivative of y, all the way through the first derivative of y and the function y itself. So there's two things that you need for the differential equation to be linear. One, y and its derivatives can't be raised to a power other than 1. In other words, they need to be linear. So if I take and make this y squared, I have a nonlinear differential equation. If I take the nth derivative of y and I raise it to the third power or the half power, then I would have a nonlinear differential equation. So when I look through this at y and its derivatives, the key thing to notice is that none of those are being raised to a power. I just have the straight derivative, the nth derivative, n minus first derivative, not being raised to powers. So that's the first criteria. And then the second criteria is that these coefficients, the coefficients on y and its derivative, the coefficients on y and the coefficients on the derivatives of y have to be functions of a single variable. So they can only be functions of one variable. So we're not working with, we wouldn't be working with, a function that had, a function of x and y. So as long as we meet those two criteria, that's the big idea. Y and its derivatives can't be raised to any power other than 1, and the coefficients on y and its derivatives have to be functions of a single variable. Those are the two key criteria to look through. So if I look at this differential equation here, I see that the highest derivative is 3, so it's a third degree differential equation. It is an ordinary differential equation because it has no partial derivatives in it. And then we would have to identify, is it linear or not? And so we would look at each of the derivatives and ask the question, are they being raised to a power other than 1? Which they're not. This one here is to the first power. This first derivative's to the first power. And then you look at the coefficients on each of the derivatives. Here the coefficient is a 1. Here it's e to the xy. And you ask yourself, is the coefficient a function of more than one variable? So here on the y prime term, or the dy dx, e is a function, e to the xy is a function of two variables. That makes this nonlinear. So this would be a third order, ordinary, nonlinear differential equation. And if you step down, you can see we just tweaked this slightly. Everything is the same, except instead of e to the x times y, now it's just e to the x, which means this coefficient is now a function of a single variable. The number 1 that's in front of the third derivative is a function of a single variable. So this is a third order, because the highest derivative is a 3, third order ordinary linear differential equation. And then over here, this one, you can see it's just a slight tweak again. Here's a y squared term, but if y is being raised to a power, it's nonlinear. So everything is the same. It's third order ordinary, but now it's nonlinear because the y is being squared. So again, y and its derivatives can't be raised to a power other than 1. So just kind of sneaking down through these. So here I have a second order. The second derivative is the largest derivative of, or the highest order derivative of y that I see. So it's a second order. It's ordinary because there's no partial derivative showing up, but it's nonlinear because the first derivative of y is being cubed. So we have a second order ordinary nonlinear differential equation. So here we've got the third derivative of y, the second derivative of y. The coefficient is a 1, the coefficient is a 4. So far it's looking linear. Here's the first derivative of y. Sine of x is a function of a single variable. Here I have x times y, which would be okay because the coefficient on the y is x. The coefficient on the y is x. So that would make it linear, except here I have y as an input to the tangent function, and this term right here is going to make this nonlinear. And if we tweak it just a hair, we tweak this just a hair, we have a third order, ordinary because there's no partial derivatives, and then is it linear? You look at those coefficients. Yes, 1 is linear, 4 is linear, sine of x is a function of a single variable, it's linear. Here the coefficient on the y is a function of a single variable, and then I have it equal to here's the tangent of x. So this is going to be linear. Notice if I subtract the xy from both sides, I would get the y term over on the left, and I would have just a function of a single variable x sitting over on the right hand side. So there's a big difference between taking the tangent of x and taking the tangent of y in terms of identifying whether the differential equation is linear or not. So here we have a third order ordinary because there's no partial derivatives, a differential equation, and it's going to be linear because the leading coefficient here is a 1, which is just a function of x. E to the x is just a function of x. We could subtract this y from both sides, and we get minus y equals 0, and then we would be in the form that we see up here, especially if I wrote it as plus the opposite of y. So negative 1 would be the coefficient on y. That's a linear coefficient, and equal to 0. 0 is just a function of a single variable, in this case x. So this would be a linear differential equation. So last example, we're going to run into trouble on this one again. Sine x is a function of a single variable, but now we have nonlinearity for more than one reason. We have y, the third derivative of y, in the exponent position on e, so that makes it nonlinear. We have y as an input into the tangent function. This makes it nonlinear as well.